So last time we started calculating the magnetic force on subatomic charges and showing where they came from, and then also showed you guys a little bit about the direction type stuff, which is kind of weird. So sort of just lay things out a little bit. So like suppose we had a magnetic field like this, and we had a little charge going to the right like this. We talk about how the magnetic force can't be in the direction of either one of either the velocity vector or the magnetic field vector. So the force would not be up or down, it wouldn't be sideways, the force would actually go in or out of the actual screen. Do something else. Suppose we had a magnetic field that looked like this, and we had a charge coming in from the bottom, maybe something like this. Well, the magnetic field is going in the dimension of going in and out of the screen. The charge is going up and down. So the force can't be up and down, it can't be in and out. The only dimension left is left or right. So it would the force would have to go sideways. So this can be kind of tricky, but there's this sort of the right-hand rule number 2 that I mentioned last time kicks in. Now there's different variations of this. You'll see different varieties, that type of stuff. But I'm going to show you one that I found online. And I'm going to modify it a little bit for my preference, but that's okay. And let's do that. There we go. There it is right there. Okay, there we go. All right. So this is the variation that I found online, and it's really close to what I like to use. I'm just going to change things up a little bit here. First of all, I'm going to get rid of these things here. I'm going to get rid of this for now. Get rid of that. I'm going to get rid of this. And we're going to get rid of this. We'll get back to that type of stuff in a second. Okay, so first things first, you got to find your right hand. And when you got your right hand, no big deal. I'm just going to erase this for now and get rid of that, because the first thing you need to do is you need to take your hand and do the classic make a gun type thing. Okay, so make a little tiny, handgun like you did when you were a kid. Now, this is your subatomic gun, and you are going to shoot charges. So this is your velocity vector. Your pointing finger is your velocity vector. That is where the charges come out of your gun. Okay, now, what you're going to do next is you're going to take those 3 fingers that are at the bottom. You got your 3 fingers down here. And they had one stretched out. I don't like to have one stretched out. I'd rather you guys stretch out all 3. So you're going to stretch out all 3 fingers going sort of sideways. So there'll be a right angle between your palm and your fingers. So if you point those 3 fingers sort of out sideways, I like doing all 3 because then these 3 look like the magnetic field lines, and that's exactly what I represent them with, is using my fingers to represent my magnetic field lines. So the only thing left is the force, and that's what the thumb represents, is the force vector. And your thumb and your shooting finger and your 3 fingers should all be perpendicular to each other, and this is right-hand rule number 2. And if I bring back the image that I showed you before, which is this one right here, very similar. Okay, you got the moving charge being shot out of your finger. The magnetic field line is the 1 finger. I like to use all 3 of those fingers because then they actually look like field lines to me. And then the thumb is the magnetic force going up. And that is right-hand rule number 2. Okay, and again, there's other variations where people have all the fingers pointing straight, and it's like they use their palm as the force. There's lots of different variations out there. This is the one that I like to use. I just find it easier thinking about my subatomic gun and my 3 fingers are my field lines. I just find it a lot easier. Okay, so let's sort of look at the 2 questions that we have up on the top here. If we did these ones up here, for the first one there with the proton coming from the left, so your proton is going towards the left, so this is your velocity vector, which means your gun needs to point to the right. And if your gun is pointing to the right, your field is going down, so your gun is pointing to the right, your 3 fingers that are stretched out, your 3 fingers should be pointing down because that's the way the magnetic field is. And if I do that, my thumb is pointing at my screen. my thumb is pointing directly at the screen, and that is the direction that the force would be. My force would be going into my screen or going away from me. Okay, and this, it can be a pain in the butt. It's like hand yoga. It can be really annoying. Try not to separate your shoulder or your wrist or your elbow, trying to do little positionings and stuff like that. But this is how it's done. Okay, and the second one, I'm going to start with my gun. My subatomic gun is shooting straight up. So it's pointing, my finger's pointing straight up. My 3 remaining fingers are pointing into my screen because that's the way my magnetic field is going. And my thumb is now pointing to the left. So my force would be to the left, something like that. So that's how you do it with those guys. Okay, let's try a different one. Let's draw a magnetic field. Okay, I'm going to draw some dots for a magnetic field. All right, there's my dots. I'm going to have my little charge coming in from the left. Okay, so in this one, my gun is pointing to the left because that's where my charge is going. My 3 fingies are pointing out of the screen directly at me because the magnetic field's coming out. If I do that with my right hand, my thumb is pointing straight up towards the top of the screen. My thumb is pointing this way, so this is the direction that the force would be. All right. Okay, let's try one more. And again, this takes practice and experience, and once you get it, it's not the hardest thing. You just got to get used to it a little bit. All right, so let's try this one. Let's say that our magnetic field is going to the right. So my magnetic field is going that way. And let's say my charge is actually going away from me. So there's my velocity vector like this. Any vector can use dots and X's, so my velocity is going away from me. So right there, my gun is pointing into my screen because that's where my charge is going. My 3 fingers, my 3 field fingers are pointing to the right, and that means my thumb is pointing straight down this way, so that's the way the force would go. Okay, so this is how we can use right-hand rule to figure out the direction of charges or direction of the force on charges inside of a magnetic field. It's a little bit more complicated than just with the field or against the field, like with electric fields. But once you get the hang of it, it's not that bad. Now, the only thing is, there's one slight way, you guys would call it a trick. What happens if you're using an electron? Well, if you use an electron, you can do the exact same thing, except you just use the opposite direction. So use your right-hand rule if you want to, and then calculate the force, calculate whatever, but then just flip your answer because it's negative, so go the exact opposite direction. The other thing that people do sometimes is if it's a negative charge or an electron, they will use their left hand instead. And you can do that. Some people do, some people don't. It doesn't make any difference. A lot of people just use their right hand and just flip their answers. The way I used to remember that, this is going to be terrible. I remembered using the left hand for an electron because I would call it an electron, which is absolutely hilarious, but whatever. So there's a negative charge. Use your negative hand or your left hand for negative, or just flip your answer. I usually just end up flipping the answer, so using my right hand and then flip it when it's negative charge, and you're good to go. Okay, so we'll be doing more practice with this in the questions that we do and that type of stuff. Now, there's one other sort of kicker with this, which is also totally awesome in a very, very nerdy kind of way. So I'm going to get rid of this. Let's get rid of that over there. And let's get rid of this over here. And I'm just going to move this over here for now. So don't want to get rid of it necessarily. All right, so let's start with this. How about, what if we have a magnetic field, something like this? I'll show you guys something else. All right, and here comes, it's just a proton, nice little positive charge, come like this. Okay, use your right hand rule. My gun is pointing up because that's the way my particle is going. My 3 fingers are pointing at my screen because that's where the magnetic field is going. And my thumb is pointing to the left. So my force is going to be in that direction. Okay, so the proton goes into the field, and its velocity vector is this way, and it experiences a force. I'll just draw my little charge right there. There's my charge. It experiences a force in this direction. Well, those two things are perpendicular to each other. And since the force vector is perpendicular to the velocity vector, it can't actually make it go faster or slower because they're perpendicular. All this can do is allow it to actually change direction. That's all it can do because they're perpendicular. Well, you've had this type of thing before. You guys have taken this in your mechanics because this results in circular motion. Okay, and I know you're super excited about that, but that's one of the cool things about subatomic charges in magnetic fields. Since the force is perpendicular to the velocity, when that little Q comes in here, it'll actually come in here and make a perfect circular path. Okay, it's really kind of neat in a very nerdy kind of way, which means we can take this and that force right there, this actually supplies centripetal force, and we can apply your centripetal force ideas to subatomics, and this is unique to charges in magnetic field. It's really kind of cool. So if we got even a little bit nerdier here, you know, if you've got an electric field and you have a charge inside of an electric field, you either go with the field or against the field, goes faster, slower, blah, blah, blah. That's no big deal. But if you've got a charge in a magnetic field, here I'm going to put this little charge right there. You put a charge in a magnetic field and it's just sitting there, it'll do absolutely nothing because it's not moving. But if you even just poke it to get it to move perpendicular to the field, that little charge will then move in a perfect circular path continuously, which is really nerdy kind of cool. Okay, so we will be using some basic FC ideas with magnetic fields, and it's not complicated, it's not hard. I find doing subatomics and magnetic fields way easier than electric fields because you don't have a whole bunch of forces and charges and a whole bunch of stuff like that. It's once you get the hang of it, it's actually really easy. Okay, so the next video we'll do some more practice with right-hand rule number 2, and then applying that to circular motion of charges as well.